Hi, my name is Alex Ramos. I am from Brazil. I am a professor at the Federal University of Pernambuco. I hope you are okay, are well, in this period of the pandemic we are going through. And I'd like to say thank you to the organizers by the opportunity to speak about my work. Uh, the flip motor process accepts a kind of first order phase transition. Uh, this work was developed with Leon Costa. Um, it's truly common in particle system interaction. We assume that the set of sites are constant. Okay. However, that's not the only one possible condition that you can assume. You can assume that the set of sites, the space, can change during the evolution of the process. Okay, a model, a physical model with this kind of idea has been used by Malyshev when he treat with some kind of deep questions in quantum gravity. It's truly interesting because in this moment when we assume that the set of sites can change during the evolution of the process, for example, we can have new particles appear during the evolution of the process, or you can have particles disappear, being erased during the evolution of the process. Uh, just when you change this assumption, we have new questions appear. For example, it's very common, for example, in contact process in water model, uh, we use the idea of coupling, but it is truly natural when you use this kind of methodology, this kind of concept, this concept, you consider of some way uh, one relation site by site, component by component, particle by particle. However, now you don't have the possibility of use this kind of idea to apply the concept of coupling. So one natural question is how can I uh, elaborate, uh, can I define a way to use this kind of concept to treat, to work with a particle process whose the variable are length. Okay, particles uh, can be appear or disappearing during the evolution of the process. The other interesting question that we have is when we are working with truly simple particle process with variable length, we have non-linearity. Okay, what's truly different from the most of the particle system interaction we work, uh, where the linearity is certainly present. It's not a bad thing, but we have now other kind of aspects to be explored in our study. Here we studied one process called flip motor. This is a discrete time process. Okay, each component can assume two states. To complete a time step of evolution of this process, uh, two operators will act on the system. The first one, which we call flip, is well known. Under this action, uh, every component on the state minus will become a component on the state plus with probability beta, and it will happen independently of what will happen in the other place. The second one is the operate with variable length. Okay, under its action, all the word of the kind one state plus on the left side on the state minus on the component of the state minus will erase the component on the state plus with probability alpha. That's the way we define the sequence of measures we will receive in each time step. Okay, that's our process. Now we choose to elaborate on simple illustration of our process. Imagine that we start the system, the process, in a configuration where all the components are equal to minus. Initially, the operator flip will choose, in some sense, the components where will suffer will become components on the state plus. Now we will have the action of the operator mother, so he will select some words which will suffer your action, uh, deleting, erasing the component. Among other results, we have selected some of them that we are more appropriate to expose here in this talk. Uh, the theorem 1 consider the parameter alpha belonging to the interval 0, 1. Okay, and if beta is less than a function of alpha, so the density of plus during all the evolution of the process will be less than 1. But we are able to offer a little bit more. We are able to offer another non-trivial invariant measure, okay, whose the density, the frequency of plus in this new invariant measure is less than 1. Uh, of course, if you understood well the ideas of the operator flip and the operator mother, you can see easily that the measure concentrated in the configuration all plus uh, is invariant too, and this measure we are called standard trivial. The theorem 2 gives us another kind of condition for on the parameter space. Uh, under this other condition, the process is ergodic. We have just one invariant measure, and we are all the time going to converging to this measure. Okay, so we were able to describe two regions uh, where at one of them of these regions the behavior is ergodic, and is another region the behavior is non-ergodic. It's natural to ask about which kind of phase transition we have. Okay, the theorem 3 uh, give us exactly that we have a kind of first order phase transition. Okay, what we have here is the following. Imagine that all the time you are observing the density of place on the frequency of the measure, on the frequency of the system. Okay, so for a certain region the density of place all the time will be less than 1. Okay, and for the other region the density of plus will be equal to 1. Okay, the theorem 3 is has more needs to be proved, is more technical, uh, it was necessary more attention to prove this result. We have used some ideas as Pyro's contour and the planar graphs. Uh, the first step to prove the theorem 3 was to introduce a constant length process nu. Okay? In this process, we don't have the idea of locality. You sacrifice this idea. Okay? I will give you an illustration like here. Uh, Imagine that you have selected uh, these two words, plus minus, but differently of what happened in the variable length, that these components with plus on the left side of minus will not disappear or be erased. The components will just change their states. Now we define a kind of a graphical representation for our process. Okay. In this graphical representation, as non-classical, we have now a possibility to find trapeziums, triangles, rectangles, um, but we need a little more. We are trying to use the ideas of pyros, so we need to define some types, and which will give us the possibility to create a contour. Okay, so these types in real are steps. Okay, we have some times of steps given the possibilities of apply our operator flip and the operator mother adapted to this new process new. Now if you see this picture, this figure, we have a contour, and each step in this contour, this walk, uh, use the types that we have defined uh, previously. Here we show some results from theoretical and numerical analysis. Uh, as the first one, we have our rigorous estimations. That one is related to theorem 1. The second one is relative to the ergodic region. Okay, if you remember, uh, that's the theorem 1. This non-ergodicity is one of the curves. The second one is relative to the ergodic situation. Okay, now I offer for you also some other numerical simulations uh, where the color bar on the right side is representing the density of plus during the evolution of the process. If you see well, if you remember my explanation, in one region the density of plus will be all the time less than 1. Okay, it's exactly what's happening here. And in the other region the density of plus will be equal to 1. Okay, the quantity 1 is represented here by the color white. Uh, the greatest part of the main ideas that we have used to develop this work was based on the Toom work, okay, Andre Toom work, and some main ideas you can see there. I would like to say thank you again, and take care.